Welcome back. Let's learn about cylinders in 3D space. Alright, so far in Calculus 3, we have worked with points, lines, and vectors in 3D space, and whether you realized it or not, we also worked with some surfaces in 3D space. Specifically, we have looked at two special types of surfaces, that being spheres and planes. Remember that spheres are basically just circles from two dimensions extended into the third dimension, right? The equation of a sphere was what we would expect for the equation of a circle, plus an extra term for the third dimension involving that z variable. And then for planes, these are probably the most basic type of surface that we work with. Remember that we like to think of a plane as a sheet of paper that extends forever within 3D space. And the equation of a plane involves all three variables x, y, and z, where they are each raised to a power of 1. Or in other words, all three variables are degree 1 variables. Okay, so those are the two types of special surfaces that we already know how to work with within 3D space, but there are actually more types of special surfaces that we need to look at. In particular, there are 3 more, which we will look at in the next couple lessons. But to start, in this video, we are going to look at cylindrical surfaces, or more simply, cylinders. Now, within the context of Calculus 3, cylinders refer to something a little bit different than maybe what you're used to. For one thing, these are not going to be solids. Alright, all the surfaces that we work with in 3D space are essentially thin sheets. They do not represent solids that have volume. And also, not all cylinders or cylindrical surfaces will be in the shape of a can. There are going to be a lot of other shapes. Okay, so maybe that's not exactly what you were expecting when you heard the word cylinder. You were probably thinking of one particular shape. That's not the case here. We use the word cylinders to refer to a special type of surface in 3D space. And so what those surfaces are, what a cylinder is a curve that is traced on a plane within the 3D coordinate system that is then projected along an axis. All right, and along that axis, the curve does not change. It's always going to be the same curve. In future lessons, we will look at other surfaces where the curve does change along the axis, but don't worry about that for right now. We're just going to focus on cylinders in this video, which is when you have a curve traced in a plane and you project it along an axis. And sometimes we call that curve the generating curve or directrix of the cylinder. I'm not really going to use those words too often in this video, but you may see that terminology from time to time when working with cylinders. Okay, but now let's take a look at an example. What exactly am I talking about here when I say that we have a curve traced in a plane projected along an axis? Well, if we take a look at this three-dimensional coordinate system here, we have our x, y, and z axes. And in the YZ plane, so that is the plane formed by the y-axis and z-axis, I have the trace of a parabola, or the graph of a parabola. All right, and what we can do with this trace of a parabola is project it along the x-axis. In other words, we are going to shoot it out through space in both the positive x direction and negative x direction. If we do that, we will get something like this. If you project that parabola along the x-axis, you will get this surface that we would call a cylinder. Now, just like when we draw curves in 2D space, like with this parabola, we just draw enough to get an idea of the shape of the graph, right? We draw these little arrows here because this curve would extend forever in these two directions. When we draw a cylinder in 3D space, and when we draw other surfaces as well, we just draw enough to get an idea of what the actual surface looks like, okay? We don't draw everything because you really couldn't, it would extend forever. And so that's what's going on here. I drew a couple projections of that parabola along the x-axis and connected them to form this cylinder. However, it would extend forever in each direction along the x-axis, and it would extend forever in the direction of the arrows of the parabola. All right, so that's the idea of what a cylinder is in 3D space. Now, something to be aware of is that not all cylinders will be projected along the x-axis like we did here. We don't have to draw a trace in the YZ plane, and project it along the x-axis, we could also draw a trace in the xy plane or the xz plane and then project along the axis that we didn't use. That's sort of what's going to happen with all these cylinders. We're going to have a curve that is traced in one plane, and then we will project it along the axis that was not involved in that plane. And you're going to see that more explicitly as we look at how to actually graph these cylinders in 3D space. And so in order to discuss that further, let's talk about what the equations of these cylinders look like. When we work with cylinders in 3D space, their equations will involve two variables. So that means two of the three of x, y, and z. You're always going to have two of those three, and that equation will give you a trace of a curve that will be in the corresponding plane to those two variables. And then you will project that curve or direct it along the axis of the missing variable. All right, so what do I mean by that? Well, let's take a look at a couple examples. Let's start with this one right here. We have z equals y squared. This is the equation of a cylinder because it involves two variables, right? Just y and z. There's no x, it is just y and z. So we know that we are working with a cylinder. The moment that you are given an equation of a surface that only has two variables, you know you're working with a cylinder. So in this case, the trace of the curve for this cylinder would be in the corresponding coordinate plane for the two variables present in the equation. In this case, that is y and z. So the trace, or the curve that we would draw before projecting it, would be in the yz plane. And so then what axis would we project the trace along? Or what axis would the curve be directed along? Well, it's going to be the axis of the missing variable. In this case, we have y and z, but we don't have x, so that means our trace is going to be projected along the x-axis. And identifying these two things is going to be very helpful when we go to sketch these cylinders, which we will look at in just a bit. But before we get there, let's look at two more examples. First, let's look at this one. We have z equals 3 divided by x plus 1. This equation also only involves two variables. We have x and z, so we know that we have the equation of a cylinder, specifically one where the curve or the trace will be in the xz plane, right? The two variables that are involved in this equation will tell us what coordinate plane we will draw the trace of our curve in order to graph this cylinder. All right, so this time our trace will be in the xz plane. And then what axis will that curve or that trace be directed along? Well, what variable is missing in our equation? We have x and we have z, so that means that this curve will be directed along the y-axis. All right, so that would be the axis that we would project our curve along to generate our cylinder. Now finally, let's look at this example. We have x equals y cubed plus 1. In this case, we also only have two variables, x and y. So once again, we know that we are working with the equation of a cylinder. There is no third variable, we only have two, so it must be a cylinder. In this case, our two variables are x and y, which means that the curve that we would draw would be traced in the xy plane. So we will have a trace in the xy plane, and then we will project that curve or project that trace along the axis of the missing variable, which in this case would be z, right? We have x and y, but z is nowhere to be found, so it would be directed along the z-axis. Okay, so that's the idea here. The equations of cylinders always involve two variables. The trace of the curve will be in the corresponding plane to those two variables, and the curve will be directed along the axis of the missing variable to create the cylinder. Okay, so now that we've established that, we know what the equations of cylinders look like and what they tell us about the cylinder. Now let's actually put these things into practice. Let's use them to actually sketch some cylinders in 3D space. First up, we want to sketch the surface z equals 9 minus x squared. Now it's very important to see here that this doesn't say sketch the cylinder. Oftentimes you're not going to be told explicitly whether you're working with a cylinder or some other type of surface. You are going to want to be able to identify that yourself. So that's why it just says sketch the surface. It doesn't say cylinder because I want you to be able to recognize when an equation represents a cylinder versus any other type of surface. And in this case, if you look at this equation, we have two variables, x and z. We don't have all three of them. Y is missing, so this is an equation of a cylinder. All right, in particular, we know that the curve we're going to draw will be traced in the xz plane because those are the two variables in the equation. So our trace is in the xz plane. And then what axis would the curve be directed along? Well, it will be the axis of the missing variable. In this case, we don't have y, so we will be directed along the y-axis. Okay, so those are two very important things that you want to identify before you try to graph anything or before you try to sketch the cylinder. If you don't know these two things, it's going to be very difficult to draw an accurate sketch. All right, but now that we have identified these two things, what we want to do is try to draw the trace of the curve in the xz plane. All right, and so do you recognize the shape of the curve that this equation represents? Does it look familiar? Well, what we have here is a parabola. Maybe it would be helpful if I rewrite it this way. If I reorder these two terms, we would have z is equal to negative x squared plus 9. And now maybe this looks a little bit more familiar. Maybe now you can see, oh yeah, that is a parabola. We have negative x squared plus some other terms. And so this would be a parabola opening in the negative direction, right? Because we have a negative in front of the x squared. So it will be opening downward, not upwards. And then this plus 9 just tells us to shift it up 9 units along the axis that we are going to be drawing it along. All right, so in this case, that would be the z-axis, right? In algebra or within a 2D coordinate system, when we would have y equals negative x squared plus 9, this would tell us that we have a parabola opening in the negative direction on the y-axis, and we would be shifted up 9 units on the y-axis. So in the same way, this is telling us that we have a parabola in the xz plane where it's opening in the negative direction along the z-axis, and we are shifting it up 9 units along the z-axis as well. All right, so identifying those things is going to help us draw the trace of this curve. Now, I just want to write down a couple important points here. As I just said, we know that the curve is going to be shifted up 9 units along the z-axis. This actually tells us our z-intercept. From this, we know that the z-intercept would be the point 0, 0, 9, right? This would be the point where the parabola would cross through the z-axis. You could always find this algebraically by setting x equal to 0. If you set it equal to 0, you'll get z equals 9, so that's how we get this point. X and y are both 0, but z is 9. And then let's also try to find our x-intercepts here. That might be helpful as well. So if we set z equal to 0, we'd have 0 equals negative x squared plus 9. And then adding x squared to both sides gives us x squared equals 9. So x is equal to plus or minus 3, right? We take the square root of both sides, and the square root of 9 would be plus or minus 3. So that gives us two x-intercepts of this. Our x-intercepts are going to be 3, 0, 0, and negative 3, 0, 0. All right, so let's plot all those points. Let's start with the z-intercept. I'll say that this right here is z equals 9. So our z-intercept would be right there. And then we want to label x equals positive 3 and x equals negative 3. Remember that the positive direction of the x-axis is this part right here. Back here is the negative direction. So I'm going to say that right here would be x equals positive 3, and right here is x equals negative 3. So we'll have a point there and a point there. Those are our two x-intercepts for this parabola. And now we can draw a pretty nice sketch or a pretty nice trace of the parabola in the xz plane, right? The plane formed by the x and z axis. If we just connect these points, which I'll do like this, make sure to add in those little arrows so that we know it goes on forever. That would be the trace of our parabola in the xz plane. Now what we want to do is project that parabola along the y-axis, right? The axis of the missing variable. So we want to project it along the y-axis, and the way we do that, the way that we can actually sketch that, is first by drawing some lines parallel to the y-axis at important points along this curve. Essentially, any points that you may have found, such as intercepts, or really anywhere along the curve. Just pick a couple spots along the curve to draw some parallel lines to the y-axis. And then once we have those lines drawn, we will just draw some more traces of the parabola. All right, so let me draw a couple of these parallel lines. I'll draw one through the z-intercept, and then two more through the x-intercepts, just like this. And now what I'm going to do is draw two more traces of the parabola along those lines where it hits the same points, right? This curve is going to remain the same as it is projected along the y-axis. So I'm going to try to draw the same parabola here, but just shift it over a little bit in this y direction and then in this y direction. So I'll draw one here, and I'll draw another one right here. Okay, so those are my two extra traces of the parabola to show that we are projecting it along the y-axis. And then what I'm going to do is just clean it up a little bit. I'll just erase this and this, a little bit of that. And then we can shade in our cylinder to make it pop out a little bit. Okay, so there we go. I shaded mine in a little bit. It's not a perfect sketch, it's not a perfect drawing, but it does get the point across. If it's still kind of hard for you to visualize what we just drew here, if you can't really see the cylinder or this sheet in the shape of a parabola, I will have a 3D render up here on the screen for you to look at. I'll put that up for a couple seconds so you can sort of see the shape that we just drew. It is hard to draw 3D shapes on a 2D surface, so don't beat yourself up if your drawing looks ugly. As long as you get the trace down and draw some parallel lines and then draw that trace again along those parallel lines, that's going to be good enough. It gets the point across of the cylinder represented by the equation you were given. All right, but that's going to be the process that we use to sketch cylinders in 3D space. You want to identify where you will draw a trace of the curve based on the variables in the equation. You then want to identify the axis that you will direct that curve or that trace along, and then you want to try to draw that trace or that curve by recognizing the curve represented by that equation. In this case, it was a parabola. And then you want to find some important points for that curve to help you draw a sketch of it, which then you can project along the appropriate axis by drawing some lines parallel to that axis and then drawing a couple more traces. And then shading in your cylinder is optional. You don't have to do that. I like to do it because it sort of makes the surface pop out a little bit. It's easier to sort of see what we're trying to draw. But again, that's optional. You don't have to do that if you don't want to. Okay, but now let's look at another example. Let's sketch another cylinder. Hey there, real quick, before we get to the next part of this lesson, if you find my tutorial videos here at JK Math to be helpful, then I'd invite you to join my membership site JK Math Plus, where you get access to many perks including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I will have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. Here we want to sketch the surface represented by this equation, 4x squared plus 16y squared equals 64. All right, now before we do anything, is this a cylinder? Well, the answer is yes, because we only have two variables in this equation. We have x and y. So what that tells us is that the trace of this cylinder will be in the xy plane. All right, so let's write that down. The trace is in the xy plane, and then z is the variable missing from this equation, so we know that we are going to be directed along the z-axis. All right, so once we draw the trace of this cylinder, we will then project it along the z-axis. All right, and so what is the shape of our trace, or what type of curve do we have here? Well, you might have noticed that both x and y are squared, and so if you remember from pre-calculus, or sometimes it's taught in calculus too, I don't really do it in my Calc 2 series because I sort of see it as a pre-calculus concept, but when you have x and y squared in an equation, you are working with a conic section. What type of conic section depends on the actual form of the equation. So it could be a circle, it could be an ellipse, or it could be a hyperbola. In order to actually determine which one of those we are working with, you want to get the equation in standard form, which we can do by dividing both sides of the equation by this constant. You want to get a constant of 1 on this side of the equation. You want to have your x squared plus y squared term equal to 1. That will give you the standard form for the majority of conic sections. So if we do that here, if we divide each term by 64, we will have 4x squared divided by 64 plus 16y squared divided by 64 is equal to 64 divided by 64. And then 4 divided by 64 reduces to 1/16. So we have x squared divided by 16 plus 16y squared divided by 64. 16 divided by 64 reduces to 1/4. So we have y squared divided by 4. And then, of course, 64 divided by itself is 1. All right, so now we have the standard equation of a conic section. In particular, this is the equation of an ellipse. We have an x squared term plus a y squared term equal to 1, and the denominators of the x squared and y squared terms tell us very important information about that ellipse. If these two numbers were the same, then we would have a circle, but since they're not the same, it's an ellipse. In this case, the distance from the x-axis that the ellipse will travel will be the square root of 16 in each direction, so that would be 4. So in this case, our x-intercepts will be at x equals plus or minus 4. And then in the same way, the square root of the denominator for the y squared term will tell you how far along the y-axis we need to travel, or in other words, the y-intercepts of the ellipse. So the y-intercepts in this case would be y equals plus or minus 2, right? That's the square root of 4, and of course 4 is the square root of 16. Okay, so now we could go ahead and draw the trace of this ellipse in the xy plane. But before I do that, a quick side note, we are going to be referencing and working with conic sections a lot in this part of Calculus 3. So if you're not familiar with your conic sections, or if you forgot them a little bit, now would be a good time to go back and review those concepts. I will have a little bit of review at the end of this video. I'll talk more about that later. But if you don't remember what the equations of circles, ellipses, hyperbolas, and even parabolas, if you don't know what those equations look like and how to graph them, you might want to go back and refresh your memory on those concepts, okay? And like I said, I'll show you a little bit of that at the end of this video. But back to sketching our cylinder here, the trace in the xy plane is going to be an ellipse. I forgot to write that down. What we did here is get the equation in standard form, and what we found is that it is an ellipse. All right, so we have x-intercepts at plus or minus 4. So I'll say that this right here is positive 4 for the x-axis, and this is negative 4. And then we'll say that this is positive 2 along the y-axis, and this is negative 2. All right, that is going to be for our y-intercepts. So then, if I draw a point at each of those intercepts, we can see the points that we would have to connect to draw our ellipse. So I'll do that here. And now that we've drawn that ellipse, what we want to do is draw some lines at those important points that are parallel to the axis the trace will be directed along. In this case, we are going to be directed along the z-axis, so we want to draw some lines parallel to that z-axis. All right, so that's what I'm going to do here. I'm going to draw a line parallel to the z-axis through each of those points that we drew along the x and y axes. And then, with the help of those parallel lines, we can draw a couple more traces of our ellipse here. We can draw one up here and one down here to really get a picture of the sketch of this cylinder. So I'll do one up here. It's close enough. It's not perfect, but that'll do. And then I'll draw one down here. Okay, once again, not a perfect sketch, not a perfect drawing, but it'll do. What I'm going to do now is just sort of clean it up a little bit, erase some of these excess parallel lines that we don't really need to make it look a little bit prettier. The cylinder would extend in the positive and negative z directions, but to be able to see the actual shape here or the actual cylinder, it does help to remove some of those lines and then of course shade in the cylinder. Okay, and so there we have it. That is going to be my sketch of this cylinder. And this is probably pretty close to what you were initially thinking about when you saw the word cylinders. You were thinking of some shape like this that is a little bit like a can. Now, this is not a perfect circle, this is an ellipse, so it's a little bit of a stretched can, but this is maybe more what you were expecting when you heard the word cylinder, okay? So yes, you will see some shapes that do actually look like what you think of when you hear the word cylinder, but not all of them are going to look like this. Some will look like our previous example, where we have a parabola projected through space, not necessarily a circle or an ellipse. All right, and once again, if you're having a hard time visualizing the surface that we sketched here, I will have a 3D render up on the screen for you to look at so that hopefully you understand what we're actually drawing here. Remember that none of these cylinders that we are drawing are solids. They do not have volume. There is nothing inside of them. This cylinder is hollow, even though it's an enclosed cylinder, meaning that the trace is an ellipse, it's a closed curve. There is nothing inside of that cylinder. It is a flat sheet or surface that has a trace of an ellipse in the XY plane. Okay, but with that, that is it for this example. Let's take a look at one more. Let's sketch one more cylinder in 3D space. Here we want to sketch the surface represented by this equation. We have z equals sine of y, where y is between 0 and 2 pi, or it's greater than or equal to 0 and less than or equal to 2 pi. All right, now first things first, do we have a cylinder here? The answer is yes, because we have an equation with only two variables, in this case y and z. There is no x is missing, we just have two variables, so this will indeed be a cylinder. So in this case, since we have y and z in the equation, the trace of the curve that we will draw will be in the yz plane. So the trace is in the yz plane, and then the x variable is missing, so we will be directed along the x-axis. Okay, so those are two very important things to identify here. Now, what would the actual curve or trace look like in the yz plane? What do we have here? Well, we just have a basic sine function, right? We're just going to have a sine wave using the values of y between 0 and 2 pi. And this will be pretty easy to graph in this case because we're going to be working with the yz plane. So that would be the plane formed by this axis and this axis. So really it's no different than working with the y and x axis in 2D, right? We're not working with the x-axis that is kind of coming out and going into the page. We're working with the y-axis and z-axis that are directly on the page. So drawing this curve shouldn't be too bad. It's going to feel like drawing any other 2D curve we've done in the past. And so if you're familiar with the sine function, you know that it never goes above the value of 1 or below -1 along the vertical axis, or I guess the axis of the dependent variable. Usually when we're working with sine, we have y equals sine x, but in this case it's z equals sine y. So instead of going up to 1 and -1 along the y-axis, we're looking at 1 and -1 along the z-axis. And then along the y-axis here, we're only going to be working with positive values of y from 0 to 2 pi. So obviously 0 would be at the origin, but then let's mark pi and 2 pi. I'll let this be 2 pi, and then this right here will be pi. And then remember what the sine function looks like, or what a sine wave looks like. You start at the origin, you go up to the value of 1, come back down to pi, you cross through that axis, go below it to -1, and then you come back up to 2 pi. All right, so our curve or our trace will look something like this. All right, not perfect. Once again, it could be drawn a little bit better. Let me just rewrite this label. I sort of drew over it. This is 2 pi. And in this case, I'm not going to draw any arrows. This is actually the entire curve because we're only working with y values between 0 and 2 pi. So we don't need to draw any arrows. I will plot some points along the y values that we did label though. So I'll put one at y equals 0, and then y equals pi, and y equals 2 pi. That just sort of helps the curve pop out a little bit. And so this is the sine wave, or the curve represented by z equals sine y. Now what we have to do is project it through space. Specifically, we want to project it along the axis of the missing variable, which in this case is x. There is no x in this equation, so we want to direct it along the x-axis. So now this is where it gets tricky. remember that we want to draw parallel lines through our curve at important areas or important points, basically anywhere, but the idea is that you want to draw lines through the curve that are parallel to the axis the cylinder is directed along. So the x-axis is going in this direction, so you want to draw lines in that direction. Don't draw lines parallel to the y-axis or z-axis. Make sure that they are parallel to the x-axis. All right, so here's what that looks like. I'm going to draw one up here, and then I'll draw one through y equals pi, y equals 2 pi, and then this one right here, that would be at the point where y equals 3 pi divided by 2. So I'm going to draw a line here, and then here, and right here. Okay, and then all I'm going to do is just redraw this curve a couple more times. I'll put one over here, and then we should have the sketch of this cylinder. So following how we drew the other one, we'll start down here, we'll come up, and then we'll come back down through this point all the way down to this line, and then we'll come back up to this line, right? That's exactly how this curve was drawn. We started at the x-axis, we came up to this line, we came down through this line, all the way down to this one, and then back up to this one, okay? So that's one of the traces, and then let's draw one over here. I'll do the same thing. We'll start at the x-axis, come up to this line, go through that line, all the way down here, and then come back up to this line. And then I'm just gonna clean it up a little bit, just like I did with our other sketches. You can erase this line to here, this one to there, this one to there, and then the same thing on this side. I'll just erase some of these lines just to make it look nicer. It really makes visualizing the cylinder a whole lot easier when you do this. And then if we shade it in, you can really get a good visual of this cylinder. And so this is going to be my sketch. It's actually not too bad. I sort of impressed myself a little bit there. If yours doesn't look this good, that's fine. As long as you got down the original trace and a couple more and connected them, that's going to be fine. That's going to be enough. If you want to get a better visual of this cylinder, once again, here's a 3D render of it. This is what it actually looks like. You can see that sine wave that is being projected along the x-axis in both the positive and negative directions. All right, and so with that, this was the last example of sketching a cylinder in 3D space. But before we end this lesson, I did mention earlier that I was going to do a little review on conic sections. And so that's what I want to do right now, because it's going to be very important that you are familiar with your conic sections as we proceed through Calculus 3. Okay, so here's my quick review on sketching conic sections. That's really what you want to know here. You want to be able to identify the equations of conic sections and then how to quickly sketch them. That's at least what I'm going to focus on here, because I think that's the most important part of what you need to understand from conic sections. Remember that there are three main types. Obviously there are circles, but other than that, you have parabolas, ellipses, and hyperbolas. You're probably the most familiar with parabolas. They can either look like this or like this, depending on how the equation is structured. When you have y equals ax squared plus bx plus c, the parabola is directed along the y-axis. It will either open up towards the positive y-axis or the negative y-axis. But if you have x equals ay squared plus by plus c, or in other words, if your equation is an x equals equation, then the parabola opens up along the x-axis, okay? And then you can find the vertex of those parabolas by using these formulas. Now, if you just have y equals x squared plus some constant, sort of like what we did in an earlier example, then obviously the vertex is at the origin. But if you have a more complicated equation for a parabola, then being able to find the vertex in this way is helpful. If you're working with the first case where you have y equals a parabola in terms of x, you can find the x-coordinate of the vertex by taking negative b divided by 2a, and then of course you can get the y-coordinate by plugging that value of x back into what y is equal to, or plugging it back into the function. And then the reverse would be true for the second scenario where you have an x equals equation. You would be solving for the y-coordinate with negative b divided by 2a, and then you would plug that back in to get the x-coordinate. All right, so those are parabolas. Ellipses are a little bit easier. They are essentially just distorted circles. The standard form of the equation is x minus h quantity squared divided by a squared, plus the quantity y minus k squared divided by b squared equal to 1. If a and b are equal, if they're the same thing, then you have a circle, but if they're not, then it's an ellipse. The center of the ellipse will always be h and then k, right? Whatever value is being subtracted from x is the x-coordinate, and then whatever value is being subtracted from y is the y-coordinate. In most cases, in most problems for Calculus 3, you're not going to deal with ellipses that aren't centered at the origin. You will from time to time, but it's more common that you're just going to have x squared divided by a squared plus y squared divided by b squared. But just know if that there's some values being added or subtracted from x and y, that it's off-centered, and you can find the center by looking at those values. Okay, if you had x plus h, then obviously negative h would be the x-coordinate, and if you had y plus k, then negative k would be the y-coordinate of the center, because the standard form is assuming that you have x minus h and y minus k. All right, and then remember that the value being squared beneath the x part tells you how far along the x-axis you are stretching. So you're going to have an x-intercept at a and negative a along the x-axis. And then in the same way, the square root of the value in the denominator of the y term, or in other words, the value of b, that tells you how far you stretch along the y-axis. You'll have y-intercepts at b and negative b. At least they would be the intercepts if the ellipse is centered at the origin. If it's not centered at the origin, then a and b just tell you how far from the center the ellipse stretches to in the x and y direction. Okay, and so those are ellipses. Just make sure that when you go to graph them that you are working with their equation in standard form where it is equal to 1. Okay, that's going to be very helpful if you want to sketch an ellipse. Make sure you put the equation in standard form. That's going to help a lot. Now finally we have hyperbolas. Similar to parabolas, hyperbolas can look two different ways depending on how the equation is formed. In general, hyperbola equations are essentially ellipse equations, but where that plus sign in the middle is negative, okay? And depending on whether the x term or the y term is negative determines which of these two graphs you have. If the y term is negative, in other words, you have a positive x term minus the y term, then you are directed along the x-axis. In other words, the curves, which are essentially two parabolas, they're going to open up along the x-axis, and they will always open in opposite directions, okay? But if the y term is positive and you're subtracting the x term, then you're opening up along the y-axis. The hyperbola is directed along the y-axis. In other words, whatever term is positive, the variable with that term, that variable's axis is where the hyperbola will be directed along, okay? And then the value of a, or the square root of the part underneath the positive term, that tells you how far from the center those curves are located. All right, so in this case, if h and k are 0, then obviously the center would be 0, 0. So the curves would be a away in either direction from the center in both cases. Okay, once again, in most Calculus 3 problems, if you're working with hyperbolas for traces of a surface, they are most likely going to be centered at the origin. You're not going to have x minus h or y minus k, but it could still happen, so you do want to know what that means when you see it. All right, but that's all I wanted to review in terms of conic sections. Obviously, there is a lot more. There's a lot of other things that you can do with conic sections, but at this point, just make sure that you are familiar with them, what the equations look like, and how you can draw a quick sketch of them. All right, that's going to be important from this point forward in Calculus 3. All right, but with that, that is all I had for this lesson. If you want to practice sketching some more cylinders in 3D space, be sure to check out my examples video. I'll have it linked here on the screen. If you have any questions, please leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.